in the Department of Astronomy at the University of Toronto. So she'll be joining our ranks very soon. And Ting and I spent a nice chat before the talk today about connecting up with the Canadian astronomers. So if you get really jazzed about her science today during her talk, please reach out. Ting is very excited to kind of meet all of us and to become a part of this awesome Canadian astronomy community. So Ting is currently a joint Einstein through the Hubble program, Carnegie, Princeton, and KICP fellow. So she's got quite the lineup of awesome postdoctoral fellowships right now. She was previously, before that, a Lederman Fellow at Fermilab. And she did her PhD at Texas A&M University. And before undertaking those studies, Ting actually did a really, really interesting master's degree that I want to take just a second to try to describe to you, although I don't think I will do it justice. Ting can help correct any mistakes I make. So it's called the Space Master in Europe, and it brings together something like 40 different students from all around the world. I think they represent 25 different countries. And she did her 2 years master's spread across 4 different nations, including Germany, Sweden, France, and Japan. And so this is a really cool opportunity. Apparently she lived in 2 big houses with like 40 different people from all over the world. It sounded really super fabulous. So for students who are thinking about awesome training opportunities coming up in their future, check out the Space Master program. It sounds really fun. Prior to all of those awesome experiences, Ting did her Bachelor's of Science at Fudan University in Shanghai, China, and also some of her training before that at Fudan. So Ting is an expert in near-field cosmology. She studies stellar streams and uses stars to trace out dark matter and dark matter halos in galaxies. She's a key member in the Mauna Kea Spectroscopic Explorer, which is a major Canadian initiative. She's the chair of the Dark Matter Science Working Group. She also works very hard on the Southern Stream Stellar Spectroscopic Survey, S5, which she'll tell us about today. And she's a member of the Dark Energy Survey, DES, and the Dark Energy Spectroscopic Survey, DESI. And so she's going to talk about all of those things today, mostly the S5 survey. But if you're interested in using stars to study dark matter, Ting is an expert, a world expert, and is here to share some of that science today. So Ting, take it away.
Sorry, I don't know how to find the unmute button while sharing the screen. Okay, thanks a lot for the great introduction. And yeah, thanks for having me here and giving me visiting Miguel like virtually. And today I'm going to talk about the Southern Stellar Stream Spectroscopic Survey. And yeah, I'm going to start my faculty position in Canada next year. So I'm very excited to have more interaction and collaboration with you all. So the Southern Stellar Stream Spectroscope Survey, because it's too long, so I'm going to just call it S5 in the future. So I'm going to start with what S5 what stream is or stellar stream is. So here you are seeing a movie showing you in the simulation when a group of star or group of dark matter particles, they get close to the center of the Milky Way, they get tidally disrupted and form this long, thin and linear structure, and that's the stellar stream. So it can be either disrupted dwarf galaxies, satellite galaxies of the Milky Way, or it can be the globular clusters or star clusters of the Milky Way. And so, so the first one, the movie you see is the simulation, and this is actual data. So this is a work led by a graduate student, Nora Ship at University of Chicago. She actually is on the job market this year, so she might apply for some postdoc positions in Canada as well. So, so she led this work that's searching for stellar streams in the dark energy survey. So dark energy survey is an imaging survey in the Southern Hemisphere using a camera called dark energy camera. So its main science is for dark energy study, but the stars, which are the noise for the people working on galaxies to study dark energy, but are something interesting for us. So here what you are seeing is what Nora made, basically is to a stellar density map. So the number of stars in each pixel scanning through in distance. So here you see the distance scanning or the distance modulus. So you can see this is the footprint of the dark energy survey. We mask this area because that's the Sagittarius stellar stream. It's one of the known stream. But then if you look at this, you will see this kind of linear overdensity structure come and goes as it's going through the distance. So these are basically the area that has more stellar density counts than the rest of the area. And that's how we find these stellar streams. And so in the entire DES footprint, we find a total of 15 streams, including 13 of them are new ones. So if look at the movie again, like this one and that one are corresponding to streams. One is called Atlas, one is called Phoenix, that I will mention them later. So there are a lot of streams discovered thanks to all these modern imaging surveys. So here I kind of compiled a lot of data and then made a stellar stream discovery timeline showing the cumulative number of stellar streams that has been discovered in the Milky Way versus its discovery time. So the first one that was discovered is the Sagittarius stream in late 90s. And you also may heard of some stellar stream like a Palma 5 stream is the first globular cluster stream that's discovered because Sagittarius is a dwarf galaxy. And there are other streams like a GD1 orphan stream. But since the Sloan and the Dark Energy Survey and the Gaia, there's just a burst of the new streams has been discovered in the past decade. And here I use two different symbols. One is the one that has spectroscopic follow-up already, and the other is just discovered by lack of the spectroscopic follow-up. So you can see about only 10% of them had a spectroscopic follow-up. This is before the S5 starts, so before 2018. And why stellar streams are interesting, and there are different signs that make us exciting about studying them. So I only gonna list three of the kind of exciting signs, but there are more than that. So first is stream are kind of the intermediate phase between the fully mixed stellar halo and intact or bound stellar system like the dwarf galaxies and globular clusters. So it will tell us about the formation of our Milky Way halo by starting those streams. And so this is showing you in Johnson simulation how the streams get, how the dwarf galaxies or dark matter halo get tidally disrupted and form these streams and eventually becomes fully mixed in the Milky Way stellar halo. And the other interesting part is that the streams are very powerful probe or tracer to constrain the mass and the potential and the profile of the Milky Way. So here is a plot showing you the mass of the Milky Way M200 using various different methods. So that's kind of the different method. And you can see different, depending on the method or the work done by different group, the mass of the Milky Way can be anything between something like 0.7, 0.8 times 10 to the 12th, all the way to 2 to 3 times 10 to the 12th. So there's a wide range about the huge uncertainty about the mass of the Milky Way. And this effect to uncertainty will direct effect like the subhalo mass function, or say the satellite luminosity function of the Milky Way when we go study that. So it's important to actually know the mass of the Milky Way more precisely. And some of this work is done using the stellar streams, and so like here. And so we definitely wanted to have more streams and to use that to constrain the mass of the Milky Way. And the other one is also the one of my most interesting one is the used streams to constrain the mass function of the dark matter subhalo. So the idea is the following: if we wanted to constrain the nature of dark matter and differentiate between different dark matter models, one of the ways to measure the number of dark matter subhalos in our Milky Way. And if there's a lot of them, then we think that it's more closer to the cold dark matter regime. But if there's not a lot of dark matter subhalo in our Milky Way, then it's possible that the dark matter is warm rather than cold. So here is example that if a dark matter subhalo fly by and pass through a cold stream. So this is an unperturbed stellar stream, but originate from a globular cluster. And in the bottom one, there were two dark matter subhalo pass by, and then because of the gravitational interaction, the one that with dark matter subhalo flyby will cause this kind of density variation in those stellar streams. And so based on like the properties of the stream, we can infer like how massive the subhalo is and when did the subhalo flyby happen. And the important thing is here is that they are not only sensitive to galaxies that massive subhalo that has actually star formed and are actually galaxies, but also to the smaller subhalos that the stars never form. So they are really sensitive to the dark matter subhalo at something like 10 to the 7, 10 to the 8th solar mass, that more much smaller than the or less massive than the currently known galaxies. Okay, so that's the interesting part of the stellar stream. And for spectroscopic follow-up, observations can not only confirm these stream that we discovered in those imaging survey are real, but also provide information on the kinematics and the chemistry of the stream, and also can characterize the progenitor of the stream, for example, whether they are from a globular cluster or from a dwarf galaxy. And finally, it can help to determine those perturbation signature that I discussed in the last slide. So this is the discovery timeline I showed earlier. And here is another one showing you the discovery timeline for all the satellite galaxies in the Milky Way. There's also big jumps due to the SDSS and also due to the dark energy survey and other survey in the past decade. However, if you look at the open circle versus filled circle, about 70% of the Milky Way satellite galaxy has dedicated spectroscope follow-up to confirm they are real and to start their property. While in the stream part, it's only 10% of them that had a spectroscope follow-up before 2018. And why so many streams has not been studied spectroscopically, I think there are three main reasons. First are the stars are faint, so we need larger telescopes or aperture telescopes to observe them. Second is something different from dwarf galaxies. Dwarf galaxies are bounded systems, so usually look at one small area on the sky. But for stream, they are diffuse. They spread like over tens of degrees on the sky. So we really need a wide field of view instrument to observe them. And also because they are very diffuse, there are also a lot of Milky Way foreground stars that are not member stars of the stream, but it's harder to differentiate them without spectroscopy. So we need a high multiplicity instrument to follow up a lot of candidates and identify the members. So this come to me about when I was doing a lot of dwarf galaxy work. I won't talk about here, but I'm happy to talk to you if you're interested in. I found like, we should also follow up these streams, not only just the satellite galaxies of the Milky Way. So it came to me this telescope, the AAT Anglo-Australian Telescope. So actually it's a clone of the Blanco telescope, which is the 4-meter telescope in Chile that we used for the dark energy survey. But this one is in Australia, but it's the same telescope size. Instead of putting a camera there, they put a fiber positioner on the focal plane that has a field of over 2 degrees. So it's called a 2DF. It's a 2-degree field fiber positioner with 400 fibers. So that's kind of the focal plane. And we have 400 fibers. You can position them at the location where you think your target is at. And then that fiber positioner feed to a spectrograph that has 2 arms called AAOmega. So this high multiplexity wide field of view 4-meter telescope is very good instrument to follow up this stellar stream. And so I started this S5 collaboration in 2018. I basically visited some of my collaborators in Australia when we had a dark energy survey collaboration meeting in Australia. And I said, hey, we should start this and we should follow up all of those cool streams. So we have about 30 members in the S5 collaboration, composed of like half of the members from the dark energy survey who involved in the discovery work, and then the other half from the Australia community and help with a lot of observations. And this is our logo and website. And here the names are the highlighted in bold are the early career scientists, either student or postdoc that might looking for a job in the future. Okay, so just some quick note about the features about S5. So S5 use AAT plus a 2-degree field fiber positioner and the AAOmega spectrograph with 30 members in the collaboration. And so the initial start is for the dark energy survey discovery. So find these streams in the dark energy survey footprint. So we decide to follow them up. So the first proposal we put in is to follow up the 14 streams in the dark energy survey. And we're targeting stars between 15th to 19th magnitude. And as I said, AAOmega has 2 arms. So we do like a median res spectroscopy at the calcium triplet region between 84 to 8800 angstrom. And then there is another arm where we're looking at a more low resolution in the bluer wavelengths. And the goal is to measure the stars of the candidate stars in these streams to a radial velocity position. So RV stands for radial velocity position to 1 to 5 kilometers per second. And I think it's a good time to start this in 2018 is we do the target selection using the high precision photometry from the dark energy survey data, which was used for the discovery. And also at the same time, that's the time that the Gaia DR2 came out. So we can use the data for the proper motion, or use the proper motion for the selection. So here's just example how we select how the Gaia DR2 proper motion can help. So this is in the proper motion space along the stream phi1 and perpendicular to the stream phi2. And so when we do some color selection and spatial selection, we can find a strong signal in certain area that in the proper motion space that the star are clumped. And if we select an area that has no stream, then we don't see that overdensity. So that's how we measure the proper motions of each stream. And after we identify that, we only need to observe stars in that red box, and we can eliminate all the other Milky Way foreground star. So that's largely improved efficiency of the target selection that was a big problem in the past, that because the candidate stars are too many, that it's hard to get a good selection. So these are how the data looks like. Again, the blue arm and the red arm, and here we're showing several spectra from the spectra from 4 stars. And so we measure the radial velocity, the metallicity, the effective temperature, and the log G, the surface gravity, like these parameters for each star. And some of them have signal to noise as high as like 20 to 30, and some of them has only signal to noise like several, but we're able to measure the velocity and other stellar parameters. So this is the status map for 2018 after, we started in 2018. This is the status at the end of 2019. So we observed a total of 10 streams between in 2018 and 2019, which is what we released internally called IDRY, Internal Data Release 1. And so here showing you the filled circles are what we have observed, and open circles are part we have not observed at that time by the end of 2019. And each circle here is basically one field of view for the AAT telescope. And in 2020, we start to expand beyond the DES footprint. So not only observe the stream that we recently discovered, after we covered all of those open circles, we start to observe the streams, all the other streams in the Southern Hemisphere. So far, we have observed a total of 20 streams over the past 50 nights, but some of them we haven't finished them. Actually, it's ongoing survey. We are just observing, we just finished today's observing, I think 2 hours ago. So because now everything is remote. I'm visiting Miguel today, so I cannot do the remote observing. So my Australian colleagues are doing that. But yeah, we are taking data even during this pandemic because everything is remote observing. So my Australian collaborator actually is observing at home at the Siding Spring Observatory. So here is just give you an idea how it looks like. So one of the stream here is called Atlas stream. So it has 12 fields we observed. And so this is in the stream coordinates for phi1 and phi2. Each here, the circle is like roughly the field of view of the AAT. So each black dots here showing you the targets we observed. So this is in phi1, phi2, the spatial distribution of the stars we observed on the sky. This is the velocity versus phi1, and this is in the proper motion space. And here is the velocity versus metallicity. And this is the color magnet diagram of all the stars we observed. And here highlights the member stars we find in the Atlas stream through some statistical analysis. So it's kind of obvious that a group of stars clustered around -120 coulombs per second and at metallicity about -2 to -2.5. And so these are the stars of this Atlas stream. So from this data, we can use to determine the line of sight velocity of individual stars, and then we can determine the velocity dispersion of the stream, and we also can measure the metallicity and the dispersion. We also get the proper motion from Gaia. So using all of those data, we can derive the orbit of the stream, and also we can follow up with high resolution spectroscopy to determine the chemical abundance of the brightest star. And using that, we can study the progenitors. So this is just listing you what we what we have, we can do with all the data we have. And here is a plot showing you from the IDR1, the internal data release 1, the 7th stream we confirmed using the S5 data. So here are the velocity versus declination and right ascension. So, and here we are only plotting the high probability candidate stars selected with proper motion. So if it's just the Milky Way halo stars, you expect to see a large spread in the velocity because the velocity dispersion of the Milky Way halo is about 100 to 200 coulombs per second. So you do see some of these kind of big spread of some of the candidate stars. But you also see these kind of very cold, narrow dispersion stars that are the candidate, other member stars of those streams, and confirming these are real structures in the Milky Way. So like this is one stream, another stream here, and another stream here. And there is a very interesting feature as soon as I made this plot. I don't know if you noticed. So each color here is basically one particular stream that we targeted. And there are two streams here, one called Atlas stream, the blue one, another called Aluma stream, the brown one. So from this plot, the velocity versus RA, the two streams seamlessly connected. So it's kind of interesting when I made this plot. So we're wondering what it is. So let's go back to the discovery. So this is again the DES footprint, and this is the Atlas stream, and this is the Aluma stream, and that is in the distance modulus of 16.7. So the Aluma stream is a little bit distant, so it's kind of weaker signal here. And the two stream has kind of a gap. This probably is not best plot. Here is kind of a zoom in of the Atlas stream and Aluma stream at a slightly further distance, so 17.6 in distance modulus. So you can see the signal from Aluma is stronger because it's slightly distant. So it's obvious that from the imaging survey that when we discover the stream, there is kind of a gap between the two streams. And also because the Aluma stream is much distant than the Atlas stream, when we discover them, we think these are two different streams. And here is just to rotate the coordinates about 30 degree clockwise. So this is in the stream coordinates in phi1 and phi2. So this showing you the the density map of the Atlas stream here and Aluma stream. And here we overplot the stars that we confirmed as member stars in these two streams in red. So because the way how we follow them up, there is a gap here and there are two separate streams. But when we plot their velocity, this is how they look like. So again, this is spatial distribution. And here is the velocity along the stream. This is a proper motion in RA and a proper motion in DEC along the stream. So these two streams in the velocity, in the kinematic space, they're seamlessly connected. And the colors, different symbols are just showing you the different stellar population. So this is the red giant branch stars, the blue horizontal branch stars, and R Lyrae stars. So the two streams, although they have some kind of discontinuity on the morphology on the sky, but in the kinematic space, they are actually showing they are essentially one stream. And here is showing you the candidate stars selected using Gaia proper motion. So because we are following up the two streams with photometry discovery, so the gray area showing you what we have covered. But there are stars maybe here and the stars maybe here that are also member stars, but we have not get spectroscopic data yet. But this is kind of showing you this kink, or say the spur that we are seeing is real, and also these stars that kind of a larger broadening. So we call a kink here and a broadening here is also kind of real, although we would like to get more observations in this area and confirm the membership. So this is the kind of a broken stream we found using the S5 data. And this is kind of not the first one. You probably have heard of these gaps in the GD1 stream that using the Gaia data, because this stream is about 3 times closer. So Atlas stream is about at 20 to 30 kiloparsec, while the GD1 stream is about 8 to 10 kiloparsec. So it's much closer. So this one, they find, the authors find a spur kind of thing and a gap in the stream. So we think these are very interesting. The Atlas stream is 3 times further away, but have kind of similar signature as this GD1 stream. So this broken stream, what can cause this? There are a bunch of, a lot of baryonic structure that may cause this, including like, can perturb the stream, including like the bar of the Milky Way, the giant molecular cloud, spiral arms, and the satellite galaxies in the Milky Way, and the globular clusters, and maybe the progenitor itself, like when the stream form can make this. So we did a thorough study of all of those cases, and we kind of exclude all the other possibilities. The only possible one is, one of the possible one is the perturbation caused by classical satellite galaxies, especially the Sagittarius dwarf galaxy. So when we take the current proper motion, distance, and velocity of the Sagittarius dwarf and rewind orbit, we find that over about 100 realization, there are 6 realization can perturb something similarly to what we see in terms of the on-sky morphology. So basically, there are some kind of spur feature that can be produced by the perturbation from the Sagittarius. So here, the black dots are the member stars that we have observed with S5. And the blue dots are the simulated particles, and showing that it can kind of mimic the observations. However, there's still difficulty to explain in the velocity space. So this is a velocity, and you can see these are the observation, but these are the simulated data. So we are still working on it. And again, this is just about 5% of all the simulated data using the current measurement of the Sagittarius, mainly due to the uncertainty of the measurement on Sagittarius dwarf galaxy itself. It has a big uncertainty. So some of them can produce such signature, but 90% of them cannot produce any of those. So that's kind of one of the possibility. And the other thing is not a satellite galaxy, a visible satellite galaxy or visible globular cluster, but an invisible dark matter subhalo. And that's the next step we are trying to study: what kind of dark matter subhalo, what kind of orbit and mass of the dark matter subhalo can produce this kind of kink morphology on the sky. Okay, so far I talk about 1 or 2 streams, which is the Atlas and Aluma stream among the 10 of the IDR1 data we have observed in 2018 and 2019. And I showed these examples talking about how important the kinematics is and what we use to study. But that's not the only thing. So next one, I will talk about this Phoenix stream and from another perspective on their metallicity. So we measure the metallicity using the calcium triplet lines in those stellar spectra. So basically measure the equivalent width of those lines, or say the line width here, we can able to tell how metal poor or metal rich these stars are. So this is what we measured. We sum up all the calcium triplet equivalent width of all the stars in the Phoenix stream. And this is the absolute magnitude. And here is showing you all the stars from the literature in the other globular cluster ranging between -1 to -2. I think 2.5-ish. So going this way, basically going to the lower Phoenix stars, there are not a lot of them, but they are more metal poor than any of the known globular cluster that has observed in the literature. And this is another way to look at them. So the cyan histogram showing you the metallicity distribution of all the globular cluster we know in our Milky Way from the Harris catalog. And the orange histogram showing you the about 11 stars we observed in the Phoenix stream that has enough signal to noise, we can derive the metallicity. So the average metallicity of this stream is around -2.7 to -2.8. It is, and the most metal poor globular cluster we know in the Milky Way so far is at -2.4-ish. So this stream, which has the progenitor is a globular cluster, but it is more metal poor than any of the known globular clusters. So this is a very interesting result, and we published in Nature early this year, and showing that maybe we don't see any of these globular cluster, metal poor globular cluster nowadays because they are less massive and less compact, so they got disrupted at the early stage, and now we only can see the remnants, and maybe they are also the source of the metal poor star that we see nowadays in the Milky Way halo. Okay, so far I talk a lot about the stream component for the S5, but S5 is not only just on the stellar stream follow-up with AAT, it actually have other 3 components, one on high res, so it's a high resolution follow-up on those stream members. And then we use, and because of the Gaia proper motion, we are very good at our target selection. So we only need about 100 fibers out of the 400 fibers that the 2DF has. So we can use the rest 2/3 of fiber for other surveys that one we did for the S5 halo survey to study the Milky Way halo stars. So not in the on the stream members, but or stream candidates, but any halo stars that we think are interesting in the same field that stream locates. And last, we also study the low redshift galaxies. So we also observe about 100 galaxies per field, try to identify galaxies that are at a nearby universe with redshift below 0.1. So I'm gonna talk a little bit about highlight a few results that come from the high-res and halo star. I'm happy to talk about the low-Z if people are interested. So first of all, about the high-res. So the high-res is using the Magellan Mike telescope to follow up, and a VLT telescope to follow up the bright members in the stream. So among the 7 streams that we have confirmed and find all the bright members, we followed up 42 red giant stars and tried to study about 30 elements in each star. And this is the most extensive set of element abundance for stars in the stellar stream. So we measure about 30 elements here, just giving you example of the 2 of them in these 7 streams, and we compare with the background halo stars. So one thing I would like to highlight is that among the 42 stars we observed, there's 1 star in the Indus stream show extremely high abundance in European, that it is a process enhanced star that will tell us something about neutron capture elements or R-process elements. And I think this is the first star that first R-process star discovered in the stellar stream. Okay, so for the, and next I'll highlight a result from the HALO survey. So I'll first start this by tell you about what a hypervelocity star is, in case you have not heard of it. So the theory, this is from Hill's Nature paper about 30 years ago. So the prediction is that if there are a binary star that's orbiting and get close to the supermassive black hole in the galaxy center, then one star will be captured and another star will be ejected at a very fast velocity, which will be maybe observed by us, and that's the hypervelocity star. So in the S5, as soon as the ITR1 is available to all of us, we look at all the velocities of the star, and one star we find at a line of sight velocity over 1,000 kilometers per second. At the beginning, you of course think that, oh, that's probably wrong. But then we take the observation again several months later, and we also even use another different instrument to take another observation. We confirm that star is at a velocity over 1,000 kilometers per second. So this is like an A-type star. So you can see very broad lines in the blue and in the red. It has a temperature about 10,000 Kelvin. And it's an A-type main sequence star at the distance about 10 kiloparsec from us. And the line of sight velocity is about 10-20 kilometers per second. But adding the proper motion and using the distance, the total 3D velocity is about 1,700. The mass about twice of the sun. And it was ejected from the and it has an age of about a few to a few 100 million years. So this is the fastest main sequence star ever found. And what make it more interesting is because we know where the location exact the star is and which direction it's going, because we have all the full 6D information. When we rewind the orbit, we find it's exactly coming from the galaxy center. So I think this is very exciting. And here showing you, this is the galactic plane, that how confident we are, we think it's from the galaxy center. So this is the plus minus about 9 kiloparsec from the galaxy center. So the red cross showing you the galaxy center. And the black contour here showing you the 95 confidence level where we think if the ejection is coming from the Milky Way plane, so the intersect between the orbit and the plane, where it's from, and the gray one is 90%. So it is likely coming from the galaxy center. And you might heard about hypervelocity star from galaxy center in the past, but this is showing you all the other ones. So here, each color showing you a hypervelocity star discovered in the past. And again, this is a zoom out of the left panel. So this is plus minus 30 kiloparsec. So our S5 HVS1 is the tiny black circle here, while all the other ones who claim that they are from the galaxy center have a much larger uncertainty. And mainly because the other ones are found as a B star and much further in distance. This one is very close, so we have a much smaller uncertainty. Yeah, so this is the only hypervelocity star confidently associated with the galaxy center that ejected from the supermassive black hole in the galaxy center. And the other way to show you why we think this is interesting. So we assume all of these are actually from the galaxy center. We can calculate the ejection velocity. So this is showing you the velocity when the star was ejected, and these are the hypervelocity star that people find in the past. None of them is above 1,000, while this one, the ejection velocity is over 1,700. So it's much faster than any of the no hypervelocity star. We think it's very interesting. And also the ejection happened about 5 million years ago. So we think maybe it's also kind of connected to the Fermi bubble or the disk of the young stars due to that special timing. And why we found only one of the star that above, say, 15 or 1,000 kilometers per second. So there might be some supermassive black hole plus intermediate massive black hole at the galaxy center make this anisotropic distribution. So I think this discovery is very cool. It's not our main science, but actually it's the first exciting science we produced as soon as we had this internal data release. Okay, so here I covered the stellar streams and the high-res, some result from high-res, and also the very exciting result from the halo star. But we did the halo star to study like extreme metal pool stars, BHB stars, to follow up the Milky Way structure. That's what most I'm interested in. And somehow one of the BHB stars actually is a hot main sequence star, and then turned out to be this hypervelocity star. And so here I leave the conclusions for what I have talk about. So S5 is an ongoing survey that maps the stellar stream in the Southern Hemisphere. We have observed or partially observed 21 streams, and the first internal data release included 10 streams taken in the first 2 years of the survey. And the result I've showed you so far is all from the first data release, because we are still processing our data, the data we're taking in 2020. And from the stream part, the Atlas and Aluma stream, which are previously thought to be unrelated, somehow are actually one stream. And we think the perturbation is likely caused by either Sagittarius dwarf galaxy or dark matter subhalo flyby. On the other hand, the Phoenix stream is more metal poor than any of known globular cloud stream. And we are also working on other papers on some of these 10 streams for producing more exciting result. And S5 also have a high resolution program, to study the chemical abundance of member stars in this stream. And in additional to the stellar stream, we also have a halo survey and a low redshift survey. We find that the fastest main sequence star using S5 data, which was kicked away from the Galactic Center about 5 years ago. And I think these S5 give a lot of interesting science result, but also it's a good experience or precursor survey for the future spectroscopic survey, such as DESI, WEAVE, Foremost. These are all the 4-meter class telescope spectroscopic survey gonna start this year or next year. And we are planning to release our internal data release 1 from S5 at the end of 2020. And hopefully people are interested in using this data to find other interesting science result. So I'll leave you, I'll stop here. And here are the papers that has come out from S5, and I briefly mentioned at this talk. One thing I want to tell you guys, a small story, is when we originally submit the paper for the hypervelocity star, we call it the Great Escape. This is to Metallicity. And after the referee report is very positive, but the editor had an argument we shouldn't use the Great Escape because it's too fancy. So we had several back and forth. Finally, we decided to take it away. But in the archive version, we keep it, just to let you know. So yeah, so this is all the exciting science that we are coming out, and there are more papers in the future. And if you're interested in this, here is the website in case you are interested in. So I'll stop here and take questions.
All right, thanks very much. So we have a few questions. I'm going to start with Mohit, who posted a question to the Slack channel a few minutes ago. Mohit, do you want to unmute yourself and ask?
Oh, sure.
Great.
First of all, great talk. Thanks a lot for a lot of information, and I really find it interesting. So my question is, does there exist a maximum galactocentric distance till which we expect to find the Milky Way stellar streams that you have been discussing in your talk?
Right, so first of all, in the current dark energy survey, the farthest stream we find is about 40 to 50 kiloparsec. Okay, so I think there are two questions. The first is, what is the farthest stream that possibly can exist? Second is how far we can go. I think the first question is it's a bit depend on the simulations, but I think the stream can go quite farther because most of the stream that we actually discovered is not in a circular orbit, it's more in a high eccentric orbit. So for example, one of the stream, the Shanab, is part of the Orphan stream. The Orphan stream has a pericenter of 10 kiloparsec, but the farthest part not pericenter of the orbit, but the stream cross between 10 kiloparsec to 80 kiloparsec for the part we have seen. So I think the stream can go pretty far away. And then the second question is how far the stream, how far we can detect this stream. I think that depends on the survey. So and also the depth of the survey. So one thing we haven't done, actually, this is what Nora is proposing for her postdoc project, is to do a selection function, or say observational selection function study about the stream and see like what is the limitation for the current data, like from DES or from PanStar. But again, LSST is going to go a few magnitude deeper than the DES, so it also will go a few another order of magnitude further in terms of detection. So I would say the current dark energy survey can find the stellar streams up to maybe 50 to 80 kiloparsec, but maybe in the future imaging survey can find even further away.
Oh, thank you. Actually, my question has a second part as well. I'm sorry. Though I think you have already answered it a bit. So what I also wondering is, what is the completeness limit of ultra faint objects using dark energy survey, specifically in the dark energy survey? Like you talked about stellar streams, but I'm thinking more about dwarf objects, dwarf galaxies, spheroidal, and all that.
So we have a paper on the dwarf galaxy selection function published early this year. So and it shows what is a detection efficiency versus distance and luminosity of the dwarf galaxy. And I would say a rough idea give you is something like 30 in terms of surface brightness is something like 30 magnitude per arc second is what we are at. And I think the LSST are going to go another magnitude or 2 magnitude deeper. But we do have detailed study in terms of the observational selection function detectability for the dwarf galaxies. But for stream, no one has done that because it's much complicated and much diffuse. That's the next project like in the future.
Thank you very much.
Okay, Adrian and Caitlin, let's go to you.
Hi, thanks for the great talk. So I was really intrigued by the part of your talk about the Aluma and Atlas streams being part of the same stream that's just been kind of perturbed. And I was really fascinated by the point that apparently you mentioned in only like roughly 5% of the simulations with, I think it was Sagittarius as the object perturbing the stream, like in only 5% of realizations could you explain some of the features of the stream, but it was challenging to explain some of the other features. Right. I'm just curious if it's been explored yet, what exact parameters of that flyby make it so challenging for that object to explain the perturbation? Is it just that you need the object to pass more closely to the stream, or is it that you need the object to be more dense or more massive? Or can you just say a little bit more about that, or what's known about those parameters?
Okay, so first of all, what we did for this particular simulation is we take the current measurement of Sagittarius dwarf galaxy, including all the uncertainties in distance and in proper motion and line of sight velocity. And then we rewind the orbit and calculate the perturbation. Only 5% of them show this kind of kink morphology. Other 95% doesn't have this kind of perturbation. And then we look at this 5, I think it was the distance of the Sagittarius dwarf galaxy is most sensitive. Basically, those 5 has a slightly different distance than the medium or average Sagittarius. So the other thing we're talking about we might do is say if this is exactly coming from the Sagittarius dwarf galaxy, then we can use that to constrain the distance of the Sagittarius dwarf galaxy better. So that's kind of a one approach. But this is to assuming like we know where are the current satellites and what is their orbit. We kind of see if they can produce these. While the other project that's currently was doing by a student working with Dennis Urkel is not like using any of no satellites, but just assuming like some kind of dark matter subhalo with certain mass and how what kind of orbit or flyby can cause this kind of kink. So it's a different how you say, angle that this is using the existing known satellites, while this is just using like a pure different, pure like a, how you say, unknown dark matter subhalo. And for that, we are trying to constrain the mass of the dark matter subhalo and also the orbit and the flyby, the impact parameter. All of those goes to this simulation, and this is ongoing work. And we try to do that so that it matches with all observables in different parameter space. And hopefully we'll find something that can explain the signature using the dark matter subhalo flyby.
Yeah, I mean, that's really interesting because I'm sure you know about like Anna Bonazza and company, like finding that to explain like the features in the GD1 stream, they have to have a dark matter halo that's more concentrated than what would have been expected from like CDM. So I'll be really eager to see the results on this and see if you find something similar. That's
right. That's so that's what we wanted to do here. Is we hope there are a lot of streams and what do I say? Yeah, we hope there are a lot of streams and a lot of these kind of signatures, so we can study them independently and see if there's anything interesting. Oh, another thing I didn't mention. So between this spur kind of and the mainstream. So in the GD1 stream, Anna's recent work, they showed no velocity difference between that spur and the mainstream. However, in our work, in this stream, I didn't have a plot here, but in the paper I do. There is in the velocity, there is some velocity difference between the spur and the mainstream. So there's kind of different from what Anna see in the other stream, but it's a different stream. So these kind of velocity variation will be key in doing all of those modeling.
great, thank you.
So it looks like Daryl has her hand up. Daryl, do you want to go ahead and unmute?
Yeah, thank you. That was a fantastic talk. So coming back to the hypervelocity star question or discovery, I am wondering if you see any evidence that that star that you've found that has such a spectacularly high velocity is a different population. I mean, you showed all of the ways in which it is unique from the other hypervelocity stars that people have posited might come from these interactions in the galactic center. I'm just wondering if you see any possibility that it could still derive from the same population, or you really think it's like something quite different than the others that have been proposed?
Well, okay. So first of all, when we say different, is really this ejection velocity. So for every single hypervelocity star candidate, right, the people I discovered, basically you can calculate the velocity when it's ejected. So this is the only kind of difference I would say that we find from the other ones. But the other one is kind of, and I think there is some observational bias. So for the hypervelocity star survey, originally started was mostly doing B stars, just hotter and bluer stars. And just because there are a few of them and they're doing these one by one. So if you are looking at the B stars and at certain brightness, so you are looking at like more distant stars. So those stars are more, are hotter and are farther away and have larger distance uncertainty. And when you rewind orbit, it also have larger uncertainty where it originated from. But that doesn't mean the population itself is different. I mean, to me, most of the hypervelocity star was B star is really a selection bias because they start with the hotter star or rare star. But there's no theory saying hypervelocity star cannot be a cooler star. And it probably it's mostly, I mean, most of them are young stars, which is also the case for this one. But I think what makes this one unique is one is because it's closer, it's only 10 kiloparsec away, so we can constrain the origin very well. And that's why we are certain it's from the center. And the second is the velocity, ejection velocity is so large, larger than any of the hypervelocity star candidate. So I think this makes it interesting. But in terms of stellar population, I think we only know it is A star, while most of the hypervelocity star has discovered in the past is more B star. But I think that's a pure selection bias.
Thank you very much.
Okay. There's another question on Slack from Mohit once again. So Mohit, do you want to unmute yourself and take it away?
Yeah, thank you. Yeah, thank you very much. Actually, I'm also intrigued by your discussion on Phoenix stellar stream. So I'm just wondering, so did we find any of these 18 stars like associated with carbon enhanced metal poor stellar population?
Oh, you mean they are carbon, if they are CEMP stars or not?
Yeah, exactly.
I don't remember. I mean, we have a paper actually. So as I said, for AET, so this is to look at the velocity and metallicity. So this is a paper purely based on the AET medium low res data. And then we do the high res next step. So there is a paper on the Phoenix stream high res to follow up the brightest stars. So those high signal to noise ones. So so we are working on a paper on that. I don't remember if there are any CEMP star there. Maybe it's no, I'm not leading that paper, but because I never heard about that. I know there is some lithium rich abundance star there, which is super interesting. That's why we decided to publish an independent paper. But there will be a paper soon coming out to study the carbon abundance and other element abundance for the Phoenix stream.
And also associated with this, related to this plot, I think SNR versus metallicity. So there is recently a sort of discovery of a very low metal poor star. I think that star is associated with Sagittarius dwarf spiral galaxy. I'm not exactly sure about its metallicity. I think it's very low. So I'm just wondering whether. Oh yeah, I think it's minus 3.0. I just check on Google. So it's minus 3.01. So does it mean that these 18 stars, they're not that unusual compared to the other subhalo?
Well, but Sagittarius is a dwarf galaxy. We know a lot of metal poor stars like -3 or -3.5 in dwarf galaxy. That's not surprising because the dwarf galaxy has a metallicity spread. So like the member stars in Sagittarius dwarf can be anything range between say -3.5 to -1.5 because it has multiple star formation history. But the globular clusters is different, right? So here we are talking about this particular stream we think originate from the globular cluster, and we are certain about that because the metallicity spread is small. Basically, the metallicity spread is consistent with the metallicity uncertainty. So there's zero spread there. So we are certain it's from a globular cluster. And so why this makes it interesting because there's no known globular cluster that at such a low metallicity. But the dwarf galaxy is a different story.
I see. Thank you.
Okay, we're nearing the end of the hour here. So if there are any more questions, we have time maybe for one more quick one. Okay, I don't see any more in the Slack window or anybody with their hands raised. So let's all thank Ting Li again for visiting us today virtually.